Our speakers this evening have a combined 30 plus years of industry experience. Let's start with the second speaker of the evening, Art Anderson, to my far right. He is the Senior Development Experience Engineer at Aerospike, and he has experience with NoSQL databases, and get this, convolutional neural networks and machine vision. Does anyone know what that is? He does. Eric does. That's over the heads of 90% of the people in the room. All right, and then the first speaker of the evening, Srinivasan, the founder and CTO of the very esteemed Aerospike, has infected many database tech things that include dozens of patents in databases and distributed systems technology. He's got over 20 years of designing high-scale real-time infrastructure experience and was previously on the IBM team that invented DB2. Very impressive. My big greatest welcome, Srini.
Thank you, Eric. And thanks for that exciting trivia session. So today, it's a pleasure for me to be here. Before I go anywhere, so how many of you have heard of Aerospike already? Okay. So just a few. So I'm going to kind of explain to you a little bit in the first part of the talk what Aerospike is and what we have been able to do in terms of enabling AI/ML applications. So that's the first part. After which Art will show you a demo on how to leverage RAG with an Aerospike application, and also take you through a multi-model application built with key value vector search as well as graph search. So you'll see how all these come together. And he'll use Aerospike as an example in these. Then we will also show you preview some features that are coming out later in the year. So what is it about AI and Aerospike? I mean, everybody knows that Gen AI is all the rage right now, and it's extremely useful in a number of applications. But AI has been around for a while. And if you look at Aerospike's development over the last 15 years since we were founded, a lot of the applications that are deployed are what you could call classical AI applications. These are predictive AI techniques, which are used for things like recommendation engines, fraud prevention, feature stores, typically used in various ad tech cases, but also in other retail use cases, for example, ad targeting, identity graphs. There was a trivia question on PayPal, for example. If you look at all of this, right, all of these are applications that have been deployed at scale over the last 10 years. So these are AI/ML applications. Aerospike is also a full-fledged database. We are also used in a bunch of other apps which are shown in the middle, right? We're used in caching, mainframe augmentations, data distribution, transaction processing, and user profile store is sometimes used heavily in machine learning AI applications also. We are talking about consumer-oriented use cases here, which have a real-time SLA. So what we are trying to do is, let's say, a number of people think something like PayPal. Somebody is trying to transfer money to somebody else, or some other transaction is happening. You could deliver a fraud score while the transaction is in progress. This is really important, because if you don't deliver the fraud score and you let the transaction go through, you might end up, from a business point of view, there is risk involved. You don't know if there's a fraud or not, and you want to also make sure that the fraud score is as accurate as possible. So accessing more data in real time gives you a better score, and then fraud actually continues to change in terms of algorithms over time. So you want to keep up with the new algorithms and counter that and so on. So there's a lot of AI/ML techniques involved in this, and it is also about getting most recent data so you can identify patterns. I'm talking about decisioning in real time, and that's basically what a lot of those top-level applications are. Now, the next part of the talk is going to talk about the technology that enables these for real-time decision-making using AI/ML techniques. Now, it's really important to understand why these techniques are important. I'll point out some of the use cases as we go along, and then we will go to the demos. The first thing about a database that is essentially a modern database is horizontal scaling or scale out. So you can actually have the traditional databases, if you look at Oracle, MySQL, and so on, they were all DB2, which I had a part in creating, essentially are all running on a single node. I mean, there's some level of distribution, but it's not a natively distributed database system. So and Moore's law helps because every 18 months or so, everything doubles, so to speak. So your machine's capacity keeps doubling exponentially. Okay, and this has been how a lot of these databases have continued to dominate over the last 3 decades. However, what happens is the current consumer-oriented applications, and everybody in the world is on a mobile phone. Everybody is trying to do purchases. They're having ads shown to them. They are playing games. Now, the rate at which data and transactions are growing is much faster than the Moore's law rate of growth of capacity. This essentially leads to having a need for horizontal scaling. And that's really important. So there's a whole bunch of technologies that we use in Aerospike to make this work. Fundamentally, at the high level, what we have is a system which is able to run with multiple nodes, but it's also able to run a system which doesn't run into hotspots. What I mean by hotspots is a particular node in a distributed system, which comprises of many nodes, becomes bottlenecked in either the CPU or the network or some other algorithms, essentially reducing the ability of the system to continue to handle the load as the load continues to increase. And this is a fundamental design point. So we are a shared nothing system which enables the system to run with no single master, and that allows you to run with, and there are lots of details here which I will skip over, but there are papers and things that we have done. You can reach out to us and we can explain more, or catch us after the meeting and we will talk to you more. There is also a whole bunch of algorithms we implemented. One of them, which is worth calling out, is a smart client. I'm talking about running potentially thousands to millions of transactions per second, all of them completing in sub-millisecond response times for getting and setting records. And in order to do that, you have to squeeze every optimization out. And one of the things that we do is to leverage the clients to also have some level of knowledge of the location of where data is. And this enables us to reduce the number of hops it takes to get to the actual data. And this makes it scale better. Additionally, we implement a lot dynamic cluster management algorithms, so you can add and remove nodes on the fly. All of this is fundamentally important to run these applications that I talked about with very high throughput, low latency, so you can make decisions for millions of requests every second, which are accurately done in the SLA that is required. And when you have to have great systems still continues to run with those kinds of throughputs. And finally, in order for that to happen, when you have a distributed system, this essentially requires data to move around. When you add a new node, you might need to fill the new node with some portion of the data from all the existing nodes. This is a long-running transaction, if you will, while at the same time you're accessing individual records back and forth from the database. So all of this requires algorithms which allow you to run in real time. So we do a lot of that. And I just spend a little bit of time on partitioning of data. One of the most important things about Aerospike and for all these AI/ML applications, because of the scale, you need to do a divide and conquer algorithm. Hyperparallelism is really important. When a lot of people are coming in and looking at different data, different users have different data in the user profile store. When you're in real-time bidding, we talked about AppNexus, our first customer. They were a pioneer in real-time bidding for display advertising. So we have a 15 millisecond loop before which you have to decide which of the bids for a particular regression bids. Essentially, a user such as one of us is sitting there either on a mobile phone these days or on the PC in the old days, and an ad has to show up. They know who you are. They then go find out what kind of interest a person may have at that time. It's not more like what news you're interested in. It's more like if maybe you just purchased a ticket to go to Hawaii, or maybe we can sell you a golf ticket, and those kinds of things go on. Okay, so all of that has to happen in real time with what's happening right there. And that kind of work essentially requires you to handle a lot of data, typically 10 billion to 100 billion entries. So we partition the data into 4K partitions. That is the scheme that Aerospike uses. And given a particular key, we can hash it to what is called a digest. And from the hash digest, we take 12 bits and basically create one of 4096 partitions. And then you take the partitions and you map them to nodes. That's what this picture shows you. So you have partitions and you have nodes. This is a 5-node cluster. So what you have here are these nodes as they are arranged on a per partition basis. When you have a 3-copy system, you take the first 3 columns, and those are the nodes in which the copies will be set. If you can also have more copies or fewer copies. Okay, that's really important to understand. And the beauty of this is when a node is either removed, in this case node 5 is removed, all of these for P2, they slide to the left. And this means that the 3rd copy will now be in node 3 and not in node 5 as it was here. When node 5 comes back on, it gets restored back to it. And all of this has to happen automatically. And there are algorithms that we have invented where we tend to balance the data equally across partitions. Balance the partitions equally across nodes. The rapidly 160 algorithm that we use for hashing automatically gives us uniform partitioning of data across the partitions themselves, the 4K partitions. But then you have to take the 4K partitions and map them to nodes. If you had 200 nodes, for example, then you end up with essentially a fewer number of partitions per node, so there could be skew up to 10 to 20%. That can be avoided by a special algorithm where you end up doing more work in terms of data migrations when you add a new node at the cost of minimizing the runtime skew in partitions. So there's always a trade-off, okay, in these things. Both algorithms are supported in Aerospike, and these are things we have learned over the time. And then cluster self-management, I already talked about. It's really important for the cluster to essentially continue to run when new nodes are added and removed. Here's an example of that. When there is a 3-node cluster with 2 copies, so each node will have 1/3 of the master partition. So I have 4,096 partitions, take 1/3 of it, and put it in each node as master partitions. It's 2 copies. You need to have a replica of these partitions somewhere else in the cluster. So you have 1/3 of replica partitions. So you now have 2/3 of the data, so to speak, on every node. A new node is added, which is typically empty when you add it, because it just doesn't have anything. Now it needs to get fed the data for both the master and the replica. So the partition map I showed you will add this node, and then it will come up with a list of essentially partition movements. So about 1/12 of the partitions will move from each node to the new node, and the other 1/12 for the replica, 1/12 for the master, 1/12 for the replica will move to the new node. At the end of all of this happens with basically no downtime. Everything is automatically figured out. The heartbeat discovers the new node, the clustering figures out what that partition map is, and then once you have that, the exchange subsystem goes partition by partition. There are limits, because when a new node comes in, if, for example, there are 20 nodes instead of 4, if all 20 nodes start sending a partition to the new node, you're going to bring down the new node before it even comes up, because it won't be able to absorb it. So all of that is actually handled by these systems there which deal with it. But at the end of this particular case, every node has 1/4 of the master partition and 1/4 of the replica, so half the data is in every node. It's really important to understand all of this happens automatically. And this is important for any of these AI/ML applications running in real time, because things have to stay up all the time. I already talked a little bit about Moore's law and how things keep increasing in terms of capacity. It could be in processors, it could be in storage, networking. All of these are doubling periodically. Okay? So scaling up is nothing but vertical scaling. One of the unique things about Aerospike is that we can both scale vertically and horizontally. Virtually everybody scales horizontally in the new modern databases. We have Mongo, they have horizontal scaling. Redis has it, Cassandra has it. Everybody has horizontal scaling. But vertical scaling is something Aerospike has really invested a lot of time and effort over the last 10 years in addition to horizontal scaling. This means the size of clusters you will see later in Aerospike are smaller in terms of number of nodes than virtually everything else. And part of it is because of what we call the hybrid memory architecture. One of the important things about Aerospike is how we leverage different kinds of storage to deliver real-time access to data. And this one shows how we leverage SSDs. This, on the right side, what you have here is a traditional database. It uses a buffer pool-based concept. The traditional database, including DB2, which I worked on very early in my career, is designed to do essentially to bring it's designed for a very slow, persistent layer. It's a block-based system. You don't directly read off of it. Okay? Everything happens by bringing a bunch of data into a buffer pool and reading from it. Okay? And that's basically this, brings it to page cache and everything, and then you read it from there. Aerospike, because of the way SSDs were developed, this is actually why we founded the company in the beginning, is we discovered that we can now do random access for reads, which means that we can get the data directly out of SSD without any of this buffer pool based, depending on the OS business. And then we also invented large block writes, because SSDs have wear leveling. You can't write to the same location too often. You will burn the location, you can't reuse it. So we do large block writes to minimize the number of writes. So this means a single write of a block can actually encapsulate thousands of actual record writes. So 1 million transactions per second running on a system could only be reduced to 1,000 writes in one block. It will only be 1,000 block writes per second. So we can handle very high write throughput and very high read throughput because of the parallel nature of how SSDs are. You can actually set up many SSDs on a node, and the data is basically based on splitting the index. The index itself in Aerospike is fully resident in memory. It's not a cache. Index is typically 64 bytes. It contains the hash digest of the right memory 160 and some other control information. So once you have a particular request for a data item, you can go to the index, find out where it is on SSD, and dispatch it in parallel on multi-threaded way. So you just go and get the data out. And this is fundamentally a game changer, so to speak, for these systems. And this is the other thing that we do. It's great that you can have SSDs, but it's also important that the transaction paths that we have implemented to basically run these single record transactions, I'll talk about multi-record later, with replication, right? So essentially, we spend a lot of time working with networking, working with multi-core, CPU pinning, NUMA pinning work, device binding. How do you take parallel network queues and bind them independently to code so the code doesn't bottleneck on network requests? There's a whole bunch of C code that we wrote, which is multi-threaded and various techniques that you use. Again, this is about modern system architectures, right? All of this vertical scaling is based on all the developments in the computer architecture of various machines. So this is an actual example of how much we can actually do. This was done a few years ago in combination with Intel. And we showed with certain kinds of networking capacity, networking technology called ADQ, that we could potentially run 15 million transactions per second on a single node. It's really interesting, and that's a really big number. Without this parallelism that networking provided, we could still get about 8.6 million, about 9 million, okay? So that is will anybody really need it? Probably not. However, when you have this huge amount of data moving back and forth, when nodes go in and out, this excess capacity that you have can process the background tasks. Because individually, nobody is running 15 million transactions per second on a single node. but they probably run like maybe 500,000, million or whatever. But the point is, the rest of it helps you in doing all of these long-running transactions. It's important to keep that in mind. So that is vertical scaling. Now, what Aerospike does with all of this is the database operations. Okay, it's a full-fledged database, which means we have to deal with various strongly consistent algorithms. This particular picture I've shown here is fairly complex. Okay, but let me kind of take you through some of the basic ideas here. The number one is you can't lose any data. So let's say a transaction is dispatched to the server from the client. The data is written. The client gets an acknowledgement that the data has been written. You can't actually lose the data after that. That's basically typically called as asset compliance. You've committed something, you can't lose it, right? And that's something which is really important. And that's basic. Every database does it. The other interesting thing is there's something called the cap theorem. So when you have a distributed system, what you can run into, and this doesn't happen in a single node system, because single node system, the system is either up or it's down. In a distributed system, you could split the network in such a way that two parts of the system could be up at the same time. So you need to have rules to ensure that even when that kind of what's called split brain, this is typically called split brain in a networking world. When you have a split brain on a database, you still have to preserve consistency, you still cannot lose data, but because of the cap theorem, because partitioning is going to happen, network partitioning is going to happen, split brains are going to happen, you can't stop it. You can either do consistency, which is the C, or preserve availability. Now, so there are cases where availability may not, it may not be possible to be up in these situations where there are enough failures. Okay, but what Aerospike has done, because of the way we have a high performance system, where I talked about scaling out, which is efficient with parallelism, and then scaling up, which takes full advantage of the hardware, including storage. We used a lot of those excess capacities I talked about to implement an algorithm where we can maximize availability in the presence of these kinds of network events. And we can afford to do that with fewer copies, for example, of the system. Now, I'll just take you quickly through this to give you the high-level point. So here is a cluster. Okay, we use a concept called a roster. A roster is nothing but a definition of what the nodes in a cluster are. Okay, that's all it is. Essentially, in this case, the cluster is nodes 1, 2, 3, 4, and 5. And that information, let's assume at some point the cluster is set up, every node knows it, they're all happy, and it's running, right? And now, that roster information doesn't change no matter whether a node is in or out, okay? That's the main thing. You can change it, but that's a separate operation. For now, this is the cluster with the node numbers 1, 2, 3, 4, 5. Now this has a split brain. Nodes 1, 2, and 3 have split, and node 4 and 5 forms one cluster. Node 1, 2, and 3 is another cluster. The important thing here is I'm showing this from the point of view of a single partition. And this partition has a replica in node 4 and a master in node 5. Let's assume it's all current, everything is going fine. In this particular case, one of the rules that we have is this partition is only active here and not active here. Even though this only has two nodes, we have both copies, and everybody, remember, knows that this is the partition map. So these people will know that 4 and 5 should be in the cluster, but I can't reach them, so I don't have any of the copies of the partition, so I'm not going to make the partition P available here, this will be available here. And then it gets a little bit more complicated. Let's say the cluster splits into this way. It splits into a 4-node cluster with 1, 2, 3, and 4, and then the 5th node stands for itself. It's a master copy. Now the data, according to our rules, will become unavailable in this master copy, but it will stay available in this 4-node cluster. This is an important case. Okay, there are some things that we have to do though. Every time a write happens to this particular partition in this cluster, it will go to the replica which now has taken over as master, but it also has to write to another place because it's a 2-copy system. You always have to write to 2 nodes. Even though this node is not available, you can't reach it. It's not taking reads or writes. this one can write into it. And there is a lot of details here, but the point is, we can continue to run, and this partition is available in this case. This is a very important sub-case, because if you want to do a rolling upgrade of a system, you want to take down a node, but you want to continue to run the system on the remaining nodes. You can't just wait until the new node comes back up before you can let transactions through. And this really allows that. And this rule helps us do this. There's a whole bunch of other systems. There are some cases where you get, in this particular case, you split into 3 clusters, 1, 2, and 3 in one cluster. 4 is its own thing, 5 is its own thing. There is no availability for this partition. So there are cases where we will not be able to make availability, because the cap theorem will eventually win if you have enough failures. Consistency is kind of important, so we can't just do it. Okay, and also there are some additional overhead for reads when you are in this situation, because this particular new replica may not have all the data that is there in this. So you just have to make sure that you handle all these cases. So what we've done is created more higher availability with these rules for strong consistency systems. And this is simply talking about the write logic. There are some, our writes are all synchronous. The thing to remember here is, because of all the high performance work that we have done, we are able to get away with synchronous replication, always, for strongly consistent systems. So when a write happens with a 3-copy system, we will end up actually writing to both copies and the master in this case before responding to the client. That's important. So all of it is actually has to work. And so on and so forth. We also support rack awareness, which means that you can, I'll show you an example of splitting things into racks. It just creates a different failure characteristics in terms of availability. If a whole rack goes away, we can still continue to run with the other rack. Aerospike also supports sync and async replication. So far I've talked about synchronous replication for strong consistency. We also support asynchronous replications. Typically, synchronous replication is within a cluster. That's how it's implemented. Asynchronous is across clusters. So you can run a distributed system with one cluster committing transactions and another cluster basically tracking it, so to speak, in an asynchronous manner. Okay? So that is, we call that XDR, and we support that. And we support eventual consistency in that, in the case of asynchronous replication. I will summarize with an example of a synchronous application and an asynchronous application case. Okay, the synchronous application case, here is a system which is a single cluster with 3 racks and 3 copies. Okay, that's really important to understand. And then what you do is essentially, this is 3 racks and 2 copies. It's R of 2, right? Replication factor 2. So when the whole idea here is, when you actually are writing to any of these, all the writes will go to 2 areas basically. A write has to always go to the master copy, and then essentially that will then send it to, in this case, to the write area, basically, And essentially all of this means that you have more overhead for writes, because every write has to go to every, if you have a cluster distributed across the entire US, a write will be about 200 milliseconds, okay? But it will be strongly consistent, but you can actually make that work. Reads, on the other hand, because of the way it's set up, can go to a local rack, because that's the beauty of it, is like if the copy is available locally, a read can be sub-millisecond. The only trade-off you have here is the writes are slower. If you don't want to pay the price for a write, then you can use the asynchronous application technology that we have. What you trade off here is consistency, because there is a lag between what happens in one node and how it appears to the other. I mean, there's a whole bunch of detail here, but the basic idea is when there are writes coming in, we figure out what to do with the write. XDR basically takes it and sends it to the remote data center, and this is happening on one cluster basically. Okay, so that's kind of how we run the. There's a whole bunch of detail here, but the main thing to remember is it's all happening inside a single cluster where we keep track of the last update time of a record, and then based on it we know when that particular record has been shipped to the other side, and then you basically figure out how to make all of this work. Okay? And then if you look at async replication topologies, we support a fairly complex set of topologies here. That's the main thing I want you to take away from this particular slide. You can have one read-write replica, and then that's just pushing data to everything else. That's like a star topology. And this is an active, full mesh, as it's called, with one of them being passive. So you can do all kinds of synchronous and asynchronous, and everything within a cluster is synchronous, everything across clusters. Each one is a cluster in each of these clouds, and then everything across is asynchronous. And it can be two-way if you wish. I think I will kind of summarize to give you an idea of what kind of performance you can expect from all this. What you can get here is, this is actually a simple 20-node cluster delivering for 1 petabyte of data, delivering about 5 million reads and 3 million, either pure reads or 3 million reads and about 3/4 million writes on the same cluster. Okay? And this is on a I3E and AWS set of nodes. And we showed this with Intel and Amazon a while ago. But that's kind of what you can do. And things have actually become even better with i4is and i4gs, and Google now has a Z3, which you can use for these kinds of deployments. So you can actually deploy really massive amount of systems which can ingest into these AI/ML systems and deliver these real-time decisionings. And that's what the database can do. And now, I'll just stop here. So Aerospike itself is a database. I don't want to go too much into it. We talked about the high-performance storage. We talked about transactions. The only thing I want to point out here, there are two things I want to point out. One is we support multiple models. I think Art will go into that in this demo. And the other one is we work with a whole bunch of other technologies. Elasticsearch is heavily used with Aerospike, for example. We use Spark, we use Pulsar, Kafka. There's a whole bunch of connections to the rest of the world. We run on every cloud. Already, I think Eric had the whole, what are the languages we support? This is exactly the set of languages we support in terms of client languages and so on. I'll be happy to answer any specific questions on the product. But first, I think I'd like to turn it over to Art, who's probably, who's going to show you a demo on putting it all together.
Thank you, Srini. Cool. So what I'm going to kind of take you through are 3 different use cases. So 2 of which you'll have the opportunity to grab links to the code if you want to play around with these things. And then one, like Srini said, a kind of sneak peek of what's to come. Excuse me. So I'm going to start with a RAG pipeline here. So how many of you are familiar with RAG? All right, cool. So for those that aren't, RAG is Retrieval Augmented Generation, right? So this is working with an LLM. So let's say I'm working with a foundational model, and I want to ask it very specific, domain-specific questions. With LLMs, they're trained, and then basically, once released, they don't know anything that's happened between training and now, right? Or there's a good chance that the domain-specific knowledge that you're after wasn't part of the training corpus. So you can ask questions, go out to ChatGPT. I'm sure you've all asked an LLM a question at this point, and it's probably made up some wild answers that do not live in reality, right? So a RAG allows you to augment the generation through retrieving some of your own domain-specific knowledge, and we pass that along as context, right? So this RAG pipeline here is one that I built a while back. And so this is taking all of the Aerospike documentation, developer docs, blogs, our support knowledge base, basically scraping it and then turning that into like smaller chunks of data and then generating vectors on those smaller chunks of data and then storing them in Aerospike's vector database. So if you're not familiar with vectors, these are just like basically it's like a numeric representation of data, right? It captures semantic meaning. Vectors themselves don't really have, like if you were to look at one, you wouldn't be able to figure out what it was, right? But utilizing vectors in a vector database allows you to do some very interesting type of searching that can give some pretty cool results. So we'll talk about that in a moment. But so we chunk these things up. We then used an embedding model. So this is just what generates the vectors. I used one called Nomic AI. I really like that one. It's got all sorts of cool features and things like that. But basically the thing I liked the best was it has a 8K context window. So what's a context window? Well, when you're talking with an LLM or an embedding model, we have to turn our text into tokens, right? So these are like generally, you could think of it as like 3/4 of a word, right? So you break all of the text down into these tokens, and then you feed that into the LLM, where then it does its kind of prediction to figure out what the next token should be, and so on, right? With an embedding model, same thing. It's going to take all those tokens in, and then it's going to generate these vectors. So just a list of floating point numbers. 8K or 8,000 token context window is pretty big. That means you can put some fairly large chunks of data into that. And then it, by default, it generates 768 dimensions. So the more dimensions you have to a point, generally the better results you'll get. It's not 100% always going to scale that way, but what was really nice is this Nomic AI gives you the ability to kind of like slice and dice those vectors. So maybe I want to save a little bit of space at the sacrifice of some accuracy. I can use what's called Matryoshka representation learning and actually say, hey, instead of 768, let's go down to 512, or all the way down to just 64 dimensions. And when I'm talking about a dimension, I'm literally talking about the number of floating point numbers that exist in this list. That is my vector, right? So just how many kind of numeric representations exist within there. And then Aerospike is what I used to create or to store these vectors. And so this is actually kind of the newest feature for Aerospike, if you will. In a true Aerospike fashion, we went and invented a whole new way of doing HNSW. And so if you're not familiar with that, HNSW is Hierarchical Navigable Small World. And what that is basically graph layers where I'm navigating graphs to drop from a very, let's say, like sparse vertex kind of graph representation all the way down to something that's going to be a little more dense that allows me to identify kind of like nearest neighbors, right? So I'm looking at a vector. Generally what I'm going to do, like with this, we're using cosine similarity. So I'm trying to identify like angles, right, between vectors and who's the nearest neighbor to the vector that I happen to be looking at. And so Aerospike does that really fast, and it's great. And what that does is it allows me to take the documentation that I have, chunk it up, create vectors on it, and then I can write a query, right? And I can say like, hey, how do I create a secondary index in Aerospike? And what I can then do is search by creating a vector of my query and then comparing that and finding the nearest neighbor within my database. And then I'll get documentation or chunks of that documentation that give me great detail on how I do that, right? Now, the whole RAG piece of this, that's right, retrieval, now we're going to take that data, we're going to send it over to our LLM with a little bit of prompt engineering and say, hey, here's a question, here's a bunch of data that kind of probably has the answer to that question, and then I want you to summarize this and give me a response. And so this is very helpful, again, in like not allowing the LLM to hallucinate and getting that more domain-specific knowledge, and then tied it all together with a little front end there. So I'm going to pop out of this and just show you what this actually looks like. So we can ask a question like, how do I create a secondary index? Oops. And then what happens is it searches the database after it's created a vector. And then if the LLM wants to respond, let's try it again. There we go. I don't know. Google decided to not work. So this one here is actually using, I know on the slide I said I was using Gemma. This is actually using Gemini 1.5 Flash, which I found is sometimes a little better, sometimes not. Like this. How do you create a secondary index? It didn't really give us a super detailed answer. There we go. Okay, a little bit more information, right? But the key part here is these are the documents that it's pulling out as it's going in and doing that vector search, right? So if you were to, let's go back here real quick. If you were to head out to our GitHub repo that this exists in, so that QR code up at the top there, that is where you can go check out the code. The actual setup is designed to just drop in an OpenAI API key. So if you want to play with it like that, you can. But the key is that we're creating that vector database and storing those vectors in there. All right, so another look here, retail demo. So talked about this multi-model thing. We have a data set here from Kaggle. It's 44,000 fashion items. And we're using OpenAI's clip embedding model. So if you're not familiar with clip, this is a multimodal model that allows you to generate embeddings on both text and images. So I can do like text to image or image to text search. But we're going to basically create like a retail website. And we're going to tie together key value vector and graph, where then we're using all three of these models to give a pretty good retail experience for folks that are using the site. So, like I said, multi-model, we're looking at the top here. This is like a key value lookup where I have just product information, things like that. On that product page, I'm actually doing a vector search. So on the kind of main image here, I'm looking at all the similar items. And then I'm also looking at, with a graph, everybody that bought that shoe. If we aggregate like the top 10 items that they all bought together, that's what we can see down at the bottom there. So if I jump out to this, I can do something where I search like blue Nike shoes, and then I should be able to see blue Nike shoes, right? And then if I look at an individual item within here, as I'm pulling up that item, right? So like I said, this is doing like a key value lookup up here. I'm also doing that vector search down here, and then that graph traversal for, what did people who bought this also buy? And so this is all a single database. It's actually all a single node that I'm storing all of this stuff in. So this is like 100,000 customers, 44,000 items, and then you can kind of play around and see all three of them together. Cool. All right, so the last thing that we're going to look at here, this is this is brand new. So this is multi-record transactions. And so what we mean by multi-record transactions is within a strong consistency application, we are able to guarantee the accuracy of multiple records within a single write or transaction here, right? So this is a kind of fun demo that we get to build here. And this is, think like Ticketmaster, right? We call it Ticket Faster. But I want to come in and I want to buy tickets to a concert, right? Now, I don't want to put seats in my cart that somebody else has already bought, right? So what we would do here is, or what we're doing here is we're going to use multi-record transactions to guarantee that I can only put something in my cart that hasn't already been put in somebody else's cart, or potentially is being bought at that very moment, or is already gone, right? So I need to be able to see these things as they come up. So we're gonna, since I'm only one person here, we're gonna just simulate some folks. And so we'll say we've got like, I don't know, 50 workers, which is gonna be a lot. So we'll go ahead and start. And we should be able to, if the internet wants to work. No.
Having a tough time deciding where you want to stay.
Right. No, I think the internet just doesn't like me tonight.
It seems to need you to refresh every time.
So yeah, it doesn't normally. So this is full of server-sent events, and so generally you'd be able to see all of these popping up, and then not select one of these guys. So let me see if I can reset it and try again. Nope. Internet doesn't like it. Cool.
Use a socket?
Yeah, so we're right now because this is like a pre-release thing. The entire server is built in Java, so it's a Spring application that's kind of running the server backend. And then we're using server-sent events, so every time something happens. But the Spring server-sent events apparently don't like it when you access it from like a different interconnection. I'm not really sure. But yeah, so this is, and then it's a React application on the front end, pushing your results back to the server. Yeah.
Question. So I've seen like this thing before, things like this, like I'm doing AMC, like I'm trying to book a movie ticket.
Yeah.
And it'll kind of give you like a time limit. It'll be like, shut you off for
Sure.
like 5 minutes in section off. So this would eliminate the need for that time limit?
Not necessarily. I mean, like, yes, it could, but the time limit is really more of a, like, I'm going to let you keep this in your cart for 15 minutes, and then after that, it's open fair game again. So this would, you'd still want to implement some kind of like server-side timeout, things like that, but yeah.
Going to the example you gave, if a customer decides to cancel, let's see how fast will serve for it to be available for resale.
Oh, I mean, almost instantaneously. So whatever that round trip takes. Yeah.
What kind of performance testing? Like, I mean, you're talking about such high levels of throughputs and things that aren't normally tested anywhere. So how do you do your performance testing? Do you have to figure out that? Or?
Yeah. So as a company, we have an entire team dedicated to that, with probably one of the largest budgets in the company. because they spin up massive amounts of servers and then clients and then testing load on these things. But as a company, I mean, you just kind of like, if you wanted to implement this, right, you could work with us, but you would also have to just test it.
Right, so most of your performance testing for your products in-house, but then other people, you have to also deal with, unless we use your product, we have to come up with.
Yeah, I mean, we also have plenty of customers that can show that level of performance that you're getting. So really kind of depends on the use case, and we can either connect you with somebody or we can help you. Cool. Yeah.
Just so I understand, so in practice, there's like clients all over the world, they're clicking.
Yeah.
And
Well,
my own client is doing what? It's constantly receiving events from a server, or when I select a seat, it's going to go on seat, can I select that seat?
no, yeah. So in this application here, basically your front end is getting basically a broadcast of like whatever's available. So every cycle, I'm going to be able to see what's available, and if I go to select it, it'll be available.
That's in the server, the Java server does that. And
Exactly. Yep, exactly. Yeah. So no, when this works, and again, it's not, there's nothing wrong with the database or anything like that, I promise. It's this Java server that we've been kind of screwing around with. But yeah, this usually lights up like a Christmas tree and it looks pretty cool. But of course, yeah, you gotta love doing things live, right? Actually, I wonder, I had a little video of it, but I think I deleted it.
So is each box the stage?
No. So no. So this is just our like super simplified representation of an auditorium. Yeah, so think of it as like each of these are sections, and then each section has a number of seats. That's cool. Just doesn't like it. I keep refreshing. You guys can see them all.
It reminds me of my US Open ticket bike.
It's not changing stuff anymore.
Well, I have to also go in and hit start again. It's web workers that are, so when you refresh, your web workers go away. So if you let it sit for a minute.
you can refresh it in another tab.
What's that?
Maybe open another tab and refresh there. I don't know how it feels. Directly the workers in the one tab. Keep going.
Let's try it. Let's try a different one here.
Oh. That looks like
No. Yeah, so. No, so this is this is the one running in the other tab. So if we keep refreshing, but yeah.
At least there's more.
And we can pull those in, and then those will forever live in my cart.
oh yeah. Okay.
Cool. Any other questions?
Sorry, this,
Yeah.
is it implemented as a transaction on the server side, or is it a client? Like, does the client submit a list of requests, it then has to know to roll back afterwards?
You're talking for like the multi-record?
Yes.
So yeah, basically if there is, so we use a series of locks, and so if I then submit, let's say a call to the database that says, hey, change these 3 records, if those 3 records, or really any of those 3 records, happen to have a lock on them at that moment in time, then the entire transaction fails. And so what I'll get back is, some level of like error handling that'll tell me, hey, these records are already locked. You can't then do anything with that.
Right, so it's log-based.
Yeah.
It's not like optimistic.
Correct. Yeah, because this is built in strong consistency, what we call namespace. So yeah, you wouldn't have like a eventual consistency or anything like that happening with that. It either can write or it can't. Yeah.
The one thing I want to add to that is the client doesn't have to do anything. It just the API calls the server, and either the transaction commits, the server will roll back all the things.
Right, okay.
That was, I think, what you were trying to ask.
I'm just wondering if this is like workaround.
There's no workaround. This is a proper transaction API. Is that correct?
Mm-hmm.
So you just open a transaction, you start changing things, and then you say commit. And the commit may not happen because something, that's normal. But if the commit happens, you're guaranteed. Doesn't happen, the server will roll back and you can restart the transaction and try to get the seat again, for example, in this case. You may not get the same seat, you might get some other seat.
Next.
What happens if 2 different people just select the same seat at the same time? Does it randomly assign to one of them, or do they have to retry it? Like if it's down to the same exact millisecond, what happens?
I received
That's actually pretty easy. Whoever gets first to the lock holds it. And it may not be the one clicking it. If you click them all at the same time, maybe let's say you calculated it, one person clicked 3 milliseconds before the other person. But based on how the transaction appears on the server, when the lock gets taken, that one will win. And the other one will have to wait. Or retry, like you said. I mean, it's like, this is nothing different than any database. Yeah, so we do the same standard algorithms. I mean, the only thing is we are more efficient because of the performance things I talked about. But that's just speed. But the correctness is the same.
Talk about how a bot might look because of the master issues. What if a bot tries to get tickets, would it all turn yellow at
I mean, it could if they did try to do that. But then, like, some of the things that you could do with that is implement like a kind of like a bot tracking mechanism, right? So how many times or how many requests come from the same client, that kind of stuff, and then kind of shut those things down. So, but yeah, if somebody were to go in and put like every one of those in their cart at the same time, it could. But yeah, we haven't implemented anything fancy like that. Yeah.
For vector index, what kind of quantization mechanism do you have?
So for the vectors themselves, we don't do any sort of quantization on the vectors. So if you put something 768 dimensions, you're going to get 768 dimensions back. We support pretty much like vectors of any dimension though. So it's up to you really if you want to, slice and dice or reduce the precision. I think like we can.
Do you got a plan to add the quantization?
I mean, I don't know that it's like on the roadmap by any means. I know a lot of the other, so like Pinecone, for example, they have a lot of these built-in libraries where you can even create embeddings with some of their stuff directly. We support anywhere from like binary to 32-bit float, whatever in between, for the embedding like dimensions. If you wanted to quantize them, you'd need to do that on your own at this moment, but it's not to say that it couldn't be a feature in the future.
I was dealing with a very large system that had my MySQL at its base, and they're using Redis for a lot of certain functions that were in. A lot of things Redis, a lot of things were MySQL, a lot of things were hybrid. How would you introduce Aerospike in to replace that kind of data from that kind of system?
Okay. So the Redis one, that's super easy. Just use Aerospike instead. So generally, like, so with all the stuff that Srini was talking about earlier, right, we can do the same thing that Redis does at the same speed, if not faster, but we can do it on solid-state drives. We're not doing this in memory. We can do it on significantly fewer nodes. We can do it with persistence, all of that. So it's pretty, the like Redis to Aerospike jump is a pretty easy one, and pretty cost-effective and efficient. If you're trying to replace SQL, then you kind of have to look at what you're actually going to do or how you want to store your data, right? So like a SQL database versus a NoSQL database, or one of the biggest differences beyond, all the obvious stuff is just you're not working with normalized data, right? So you're generally writing, so like in SQL, we try to like normalize our data so that we can kind of write any query and get good, efficient results back from that. Whereas in NoSQL, we store the data for the query, right? So you start with the query, how do I want to get my data? What is it that I'm looking to get? And then my data model is going to be representative of that. So I might be like duplicating data because it's faster for me to grab it from two places versus one where I have to run multiple transactions, things like that. So the SQL to NoSQL jump is a little bit bigger, but if you're looking for like more efficiency and you don't have a lot of these like relationship dependent queries, right, then you could easily do that. If you do have a lot of those relationship dependent queries, then you may just want to stick with SQL. Aerospike is not like a silver bullet, doesn't or whatever. It's not perfect for every single situation, but it can help in a lot. Anywhere that you're like using Redis as a cache or things along those lines.
And one thing I want to add there is if you're using something like MySQL or any SQL database and use Redis as a cache in front of it to improve the performance based on the kind of data models that you have, you might be able to replace both the database and Redis and just use Aerospike. And this is a path many customers have followed because they were really using technologies they understood well. In fact, that's where I started when I was in a previous company. It was at Yahoo. I was building all my mobile applications on MySQL and Oracle. And then that's when we ran into a number of real-time, I would say, issues, for lack of a better term, where we couldn't service it was a very long time ago, like 2005, 2006. We had 50 to 100 million mobile customers. It looks like almost laughable right now, with everybody having 2 mobile phones. But the point is, that's what it was in 2004. So we were working on this technology before mobile became cool, and we ran into problems even then with running it on SQL data, so we put caches in front and so on. So Aerospike was invented to not have to have that kind of architecture. You just have one architecture with a database which can handle that. We don't do SQL, but a lot of the applications don't need SQL, the ones I was building for mobile. We were doing it with SQL because that's what we knew. So,
right, but I mean, there's still, right, of course.
Yeah.
Still,
But
there's
it's
still
complex.
applications where,
It's
like for instance, if I've got a lot of school district data, and I've got it like in an LTI kind of like, format. I've got structured data that's
in those cases, you're probably better off staying with SQL.
Cool. So real fast, because I think we need to wrap up here.
We got to give away the power.
Yes. So if you didn't sign up, get that QR code there, and then
Go on your Slack.
go on my Slack. All right.
Forgive us one moment. We're gonna get the raffle up.
This right here.
Yep, right there. Go in there. Okay, we have to copy and paste the names. You all are in there.
Congratulations, everyone. Good luck.
Just copy and paste it. And then it'll run it. It's kind of a fun little thing. It's okay. See it.
I bet this one will work.
Yeah, let's see.
Those are the names?
I think so.
Yes, they are. I was polite and didn't put your last name just in case.
So what do we do? Just hit
Hit
confirm?
And hit start. There you go.
Okay.
Makes you go through a few steps, but it's kind of fun. Woo! Now it better work, right?
Oh!
Justin, you're scoring everything tonight.
Nice.
He said it's gonna be me.
Oh, man.
It was breaking his favor.
Would you like to hold this up with our speakers and
Oh, what's up?
I'll take your photo and then I've got your email and stuff.
Yeah, where you want me to take it? Right here?
Right in front of there.
Right in front of you. Okay, sure.
Go ahead.